we quickly review what we did last time. That is, we considered rather we introduced you to two kind of control systems which exist in a generator. One is the one which controls the voltage applied to the excitation system, and the other control system is which controls the power input to the turbine. So, we will quickly review excitation systems. That is what we kind of began doing last time. We in fact consider two excitation systems. One is a static excitation system which does not have rotating parts and conveys the voltage through slip rings to the field of the main generator. The other kind of system is in fact a static excitation system and a brushless excitation system, in which you have a permanent magnet generator which feeds a synchronous machine, which is then rectified using a control rectifier. That output is fed to a stationary field winding of another generator whose output is available on the rotor, and that three-phase output is rectified using a diode bridge which is not controlled and fed to the field winding. The control of course is done via the this control thyristor based rectification system. The control of this brushless excitation system is done via the control signals applied to the control rectifier, and that control system is in the form, control signal is in the form of the delay angle which you apply to the thyristor based converter here. Now, thyristor based converters are most commonly used, so I am showing you that. The delay angle in turn is actually determined, it can be determined by manual control, that is you actually tell how much voltage is to be applied to the excitation system. But that is not a very good idea, because for example, a synchronous generator which is feeding a load, if the load is suddenly thrown off, the voltage at the terminal of the generator may suddenly rise. Okay. So, because of that it is a good idea to have a closed loop control of this firing angle, and that is achieved by what is known as the excitation control system, which is shown in the next slide, which is of course looks pretty complicated. The main generator and exciter are both handling the excitation power of, and the regulator in fact is only giving you a control signal, okay, which is a low power circuit, and this regulator is in fact having a reference set point for the terminal voltage of the generator, and that is what is usually done, and that through feedback control it tries to keep the voltage at the set point. Now, in addition I mentioned that you do have other control loops. One of them you see here is the limiter and protective circuits. The limiters, the aim of the limiter is of course to avoid the limits of the generator getting exceeded. For example, if the generator stator current becomes very large, in that case you may wish to scale down the reference voltage here, and that is done automatically. Similarly, if the field winding current becomes very large, you may want to reduce that as well. In such a case, you override the voltage regulation function. We shall see later when we connect the synchronous machine to other synchronous machines, there is a phenomenon called power swings. One can in fact damp out these power swings by modulating the reference voltage through what is known as a power system stabilizer. Now, one of the important points which you should note in a power system, that wherever there is a power electronic regulator, which this power electronic regulator could be at the excitation system of a generator, it could be an HVDC link, it could be a STATCOM, or it could be the voltage source converter which is interfacing a solar power system to the grid. All these are in fact these power electronic interfaces, they can be controlled quite fast, and since you can control them fast, you can use the transient abilities, means you can modulate the output of the power electronic converters to actually achieve some control objective like stability as well. So, this is something which you keep in mind. We shall get back to this when we discuss electrical power grids. Now, the regulator, if you look at it, is essentially a simple control system, which is usually an output feedback control system as shown in the next slide. So, this is of course only representative. Simple, this regulator in fact is called the automatic voltage regulator. The main thing is of course the voltage reference and the terminal voltage, measured terminal voltage. The error signal is amplified using, in this case, a proportional controller in series with what is known as a lead lag block, lead or lag block. Of course, whether it is lead or lag depends on the values of T1 and T2. You may have in your math or signals and system courses understood what this transfer function representation is, but we will quickly review that as well. And the summing junction, these are all of course implemented using electronic circuits. In fact, most of today's AVRs are in fact implemented using digital control systems, where the set point of course is set digitally and a measured terminal voltage is actually sampled, and all this is in fact, all these control algorithms or these controllers are in fact implemented using a digital control system, that is using a computer. Now, the output of the AVR is in fact to the thyristor bridge, which is in fact the delay angle. Okay. You may wish to in fact at these two summing junctions alter the behavior of the AVR. I told you some time back that in case the synchronous generator hits its limit, you may wish to in fact override the voltage regulation function. Similarly, the stabilizing functions can in fact modulate, that is during transient conditions it could actually adjust or modulate the voltage reference of the AVR. So, this is the general block diagram. Now, usually this block diagram, if you actually look into any manual or data sheet of AVR or the AVR reference manual, you will find these controller block diagrams. So, it is a good idea to simply review quickly what these controller block diagrams mean. Usually these control systems are usually linear. In fact, what you see here is a linear system within the box, but of course, it also has a limiter, which is in fact a nonlinear element. So, we will quickly just look at these blocks in a very briefly, so that you get an understanding of what they mean. Remember that the AVR, can you go back? Yeah, the AVR is in fact a control system which is implemented by us. So, we have some freedom in choosing the structure of what is shown in the green box here. We can have more complicated transfer functions so that we achieve the transient and steady state responses. Okay. So, control system design, as you may have done in your control systems course, is essentially a way of controlling a plant, and you need to have a control algorithm which will give you good response. Now, one of the simpler examples which you can think is if you go to a grain shop and you want to weigh say a kilogram of grain, okay, or rice. There are several ways to do it. Rather, one of the very brute force kind of way of doing it is to have the average weight of of 1 grain of rice, the average weight depending on the variety of the rice, and then you count the number of grains which are required, which will in fact give you the what you desire. Suppose you require 1 kilogram, you have to find out the number of grains. So, you can count them and give them. So, this is the kind of a brute force open loop kind of way of finding out kind of giving or measuring out 1 kilogram of say rice. The other way, which is much more sensible, is to have a weighing machine, and you give a set point to the weighing machine. In case it is consisting of 2 pans, you can actually put the set point, that is the 1 kilogram weight on one of the pans, and after that you may in the other pan you can pour out some rice, and the pouring out of the rice is actually mediated by a hand. Usually you kind of pick up a grain of a fistful of rice and keep on pouring it in till the set point equals the the pans essentially balance out. Now, the set point, the reference weight which you put in one pan is in fact the set point. It could be 1 kilogram in this case. Your hand is actually like an excitation system. It's an actuator. It is actually giving the muscle to actually kind of put in rice into the pan. Your eyes are in fact the sensors which actually look at the difference between the positions of both the pans and try to estimate the error signal. And your brain is in fact the controller, which after looking at the difference between the positions of the two pans decides how much you should command your hand to pour out rice, how you should, whether you should let out more rice or even and remove some rice from the pan. So, your brain is in fact a kind of controller. Untrained, if you use the wrong kind of algorithm, then you will find that you take a long time to weigh the rice. For example, if you give it to a 3 or 4 year old baby, you will find that he or she takes a lot of time to weigh the pan, get the pans to balance. The reason is simple, that the brain is not trained in a proper way, or the algorithm has not got trained in a good way so as to quickly reach the equilibrium, whereas a shopkeeper who has been doing it for many years can quickly get to the to the equilibrium. Actually, what your brain is likely to do is look at the difference between the position of the pans, and almost proportional to that, it may in fact command your hand or your fist to release some rice into the pan, or remove some of it. So, the control algorithm is your brain. So, if you actually look at this analogy, the set point is the reference weight, the pans are in fact the summation blocks or the error, they actually take out the error, the eyes are the sensor, the brain is the controller, the hand is in fact the actuator, like an excitation system, and the movement of the pan and the basic dynamics of the pan is in fact the plant. So, this is essentially how a control system is, and this is no different from it. Now, the simple algorithms or block diagrams which are used in control system, this is in fact one of the many of the algorithms are expressed in terms of continuous time transfer functions. Now, what is a transfer function? A transfer function is simply a dynamic, is representative of a linear dynamical system, and in fact, if you look at this 1 upon 1 plus st, it can be represented in fact in the following fashion. You can represent 1 upon 1 plus st as 1 upon s u minus y by t is equal to y. In fact, how does this actually come about? Because remember that if what does this s represent? S is in fact, if you have done Laplace transformation, in that case you know that this is the Laplace variable or the frequency variable. So, 1 upon 1 plus st is a transfer function between the output and the input. So, this is a representation, this is a dynamical system. Once you see an S here, of course, it contains a dynamical system, and essentially what is mean is u upon 1 plus st is equal to y of s. Now, the thing is that you can in fact, so you can write this as u is equal to y into 1 plus st into this is into y of s. Us and y of s are the Laplace transform of the input and the output, and this really boils down to u minus y upon t is equal to s into y. Now, s into y of s is the Laplace domain, this is all in the Laplace domain. This actually is the Laplace transform of the derivative of y. Okay. So, this is the derivative of y. So, what you can actually represent this quite well. So, this is plus and this is minus, and this is u and this is y, and in fact 1 upon t u minus y. If you integrate, this is equal to the derivative of y. So, if you integrate it, you will in fact get y. So, this is the block diagrammatic representation. You can also the underlying differential equation is dx by dt is equal to 1 upon t x plus 1 upon t u and y is equal to x, and this is in fact going to be x also, this is x dot, and this is what you get in fact. So, you will in fact you can represent, so this is in fact you can say that this transfer function is representative of a set of differential equations. So, in fact there are one or two other characteristics which you should be aware of, that this in fact 1 upon 1 plus st is in fact the characteristic, is a kind of a low pass characteristic. If you actually look at this transfer function, a few things can be inferred right away. The thing is that if the input is a steady value, for example, you give a step to UFS and you wait for everything to reach steady state, then the overall gain of this transfer function is given by, in steady state you can obtain the gain by putting limit s tending to 0. So, the gain is equal to 1. So, in steady state the gain is equal to 1, that is if my input is say 100 in steady state, the output in steady state is going to be 100. So, this word steady state of course is very important. So, this is the output in steady state. During transient, that is if I suddenly give a step change to u of s, then how does y change? For example, if u is 100 and let us say everything is in steady state, y is 100 and suddenly I change u from 100 to 0. In that case, y will not change suddenly. The reason is that the transient gain, which is in fact got by putting this s tending to infinity, the transient gain is 0. What it means is that for very sudden changes like step changes, y will not respond immediately. So, also if you give a input which is sinusoidal of a frequency omega, the gain and phase shift is obtained by simply putting s is equal to j omega. So, that is giving you the steady state response. So, the steady state responses, remember the word steady state is important. The steady state responses are obtained by appropriately plugging in values of s in this transfer function. So, that is one interesting way of interesting inference which can be drawn directly from the transfer function without going to the underlying differential equations which this transfer function does represent. So, remember that this transfer function actually represents a system of equations of this kind. There is no unique way of representing a transfer function by differential equations, but this is one of the ways. Now, so this in fact has got a low pass characteristic as is seen from this what is shown in your slide here. In fact, if you give a step change, you will see that y will not respond immediately because its high frequency gain is practically 0. So, a sudden change will not cause much change in y. Remember that there is an interesting correlation between what we call as high frequency behavior and transient responses. When I say something changes suddenly, an equivalent way of saying it is that it has got a high frequency component. So, when we are talking of transient response, we are in fact talking of the high frequency response of the transfer function. So, the high frequency gain of this transfer function is 0 if your frequency tends to infinity. So, a sudden change which is like having a high frequency component, this transfer function does not respond very well. In fact, so this if you give a step, y in fact takes its time to reach the steady state, which is roughly around 4 to 5 times the time constant t which is given in this transfer function, and this is what is known as the first order transfer function. In fact, if you can in fact by plugging in various values of s is equal to j omega, you can in fact get a gain and phase characteristic, and this is of course having a low pass characteristic. So, this is something which you should so usually the gain is given in a log scale. Remember that you get a nice kind of behavior almost linear in the low frequency and the high frequency range if you actually plot it in the log scale. So, this is how transfer function, this is called a first order low pass filter transfer function. Okay. So, this can be in fact used to remove the high frequency components of a signal. Okay. This 1 upon 1 plus st also may be used to represent a plant which does not respond to inputs which are say or having frequency components which are whose main frequency components are greater than 1 upon t radian per second, okay, or 2 pi by t radian per second. So, this is a rough way of understanding this transfer function. In fact, this gain kind of turns around the turning point of the gain, which will be shown from using the mouse here. Turning point of this gain is roughly equal to 1 upon the 2 pi by t is roughly the turning point or the corner frequency of this gain. Okay. Yeah. Another transfer function which you can look at as the converse of the earlier transfer function. In fact, it is not very difficult to see that this is st upon 1 plus st is in fact 1 minus 1 upon 1 plus st. So, you kind of can imagine that this transfer function behaves in quite the opposite way compared to the earlier transfer function. It has got 0 steady state gain and it has got a high frequency gain of 1. So, if you put s tending to infinity, this or high frequency st upon 1 plus st approaches 1. And if you notice that the transient response in this case is given by phase and gain plot which looks like this. I have just done it very approximately. You can just try to using simple tools to actually plot this on a log scale and see the response, and you will find that it has got a gain of 0 in steady state at very low frequencies and 1 at high frequency. Of course, although I said log scale, the 0 and 1 are not in log. Okay, what I have shown here, 1 is actually before you take the logarithm. So, in a log scale, do plot it and you will find at low frequencies the gain is 0 or in the log scale it will be minus infinity. If you actually give a step change in u, you will find that y behaves like this. So, this can be looked upon as some kind of high pass characteristic, and in fact, this kind of transfer function is used whenever you wish to remove low frequency components from the input. For example, if you want to remove any DC offset from u, you may use this kind of transfer function. Yeah. Another commonly used transfer function is a lead or lag block. In fact, if T1 is greater than T2, it is called a phase lead compensator, and T1 less than T2 is called a phase lag compensator. In fact, if you try to write this, the transfer function of this, in fact, you will find that the gain is in fact, if you put s is equal to 0, the gain is equal to 1, and if T1 is greater than T2, at some point the gain starts increasing and decreasing. So, you will find that in fact, I am sorry, this is not the gain, this is not how it looks like. In fact, when s is equal to 0, the gain is 1. This is not in the log scale, of course, the gain is 1, you just put s is equal to 0, and in the log scale this this gain of 1 becomes 0 decibel. Okay. So, that is something which you should remember. 20 log of gain to the base 10 is the decibel gain. So, this is something which you need to remember. Now, this kind of, if T1 is greater than T2, you will find that this has got a high frequency gain of T1 by T2, which you can of course obtain by putting s tending to infinity, whereas the phase in fact has got a bump like this. So, it gives a phase lead, that is why it gets its name, and of course, the amount of phase lead depends on this T1 by T1 and T2, and the frequency at which it occurs is related to 1 by T1 T2 in hertz. So, this is the center frequency of this phase lead. Now, phase lead, as its name suggests, is actually gives you a phase gives you a phase lead. If you give a step change to a phase lead transfer function, its transient gain is T1 by T2, which is greater than 1. So, you will find it goes up and goes down like this way, and this decay of course is determined by the denominator transfer function. In fact, the denominator transfer functions are important. They are called the poles of the transfer function. In fact, the poles of the transfer functions determine the kind of decay rates which you see in the responses of the transfer function to say step inputs, etc. In fact, the poles and what is known as the eigenvalues in the state space representation are equivalent, except that sometimes when you have an input output representation, sometimes the poles get cancelled off with what are known as the zeros of the transfer function. It is not happening here if T1 and T2 are not equal. Of course, if T1 is equal to T2, you will have these two cancel, and then the transfer function is simply a gain of 1. Okay. But of course, internally you may still have these dynamics which is determined by the denominator time constant, or the pole of this is of course minus 1 by T2. Okay. In fact, if the pole has got a root, or the pole or rather the denominator has got a root which is in the right hand side of the complex plane, then it means that the system is unstable. Okay. So, in this case of course, if T2 is positive, then the pole is minus 1 by T2. So, the root of the denominator polynomial, in fact, the roots of the denominator polynomial are in fact the poles of the transfer function, and the poles determine stability, of course, provided there is no pole 0 cancellation. If there is a pole 0 cancellation, then some poles may not be visible or they may not be observable at the output y, or they may not be controllable using the input u. So, if either of these two things happen, some pole may get cancelled. In fact, some poles may not get cancelled, and some poles may get cancelled with the zeros. The roots of the numerator polynomial incidentally are called zeros. Okay. So, remember these very basic points relating to transfer functions. These transfer functions are used to actually alter the behavior, transient behavior of a control system. As I mentioned, 1 upon 1 plus ST would be like a filter, it removes the high frequency components. It may also be used sometimes to model the system. So, a control system is of course something which is designed, but sometimes even a linear plant or the thing you want to control may sometimes also be modeled by transfer functions or differential equations which are converted to transfer functions. Now, remember that if it is a control system, these transfer functions may be implemented using a digital system. In fact, integration, summing and gains are usually done by op amps in analog control systems. Nowadays, analog control systems are especially if the control systems are complicated, they are rarely implemented using analog systems. Most of the AVRs which you will see in the field are in fact digital AVRs, they implemented digitally and they are essentially implementing numerical algorithms. Of course, the first step in any doing any kind of implementing any kind of digital algorithm is to actually convert the continuous time system to a discrete time system, and that is done using first of all, if you have got a continuous time signal, you convert it into by sampling into a discrete time signal, and these discrete time signals are then converted to digital form using some kind of analog to digital converter. So, you convert it into a number in some sense using a bit representation, and then once these are numbers, you can actually use a computer to do various operations including summing, multiplying, integrating and so on, and then the output can again be converted to analog form by a digital to analog converter. So, of course, so the steps in any kind of digital implementation are to, for example, in an AVR, what you would do is you would have in fact a set point which is a number which is in a computer, and this computer would also measure the terminal voltage, but this terminal voltage in fact would this would be obtained from a transducer like a potential transformer, and which will in fact be getting a sinusoidal input. The sinusoidal input is converted to digital form by first sampling it and converting it into a digital using an ADC. So, you use a sampling of this. Of course, the sampling should be fast enough so as to avoid aliasing, and you will in fact, so that you can represent this signal in a more accurate manner, you actually have to sample at high enough frequency. Once you convert it into a discrete time form, you have to convert it then afterwards into a number. So, eventually this ADC converts this each sample into a number, and this number then is fed into a computer, which in fact does this difference operation. And then afterwards, for example, if you got a proportional controller, then it multiplies it by the proportional gain, and then for example, it can give it out as the output. So, this could be done and then using a digital to analog converter, you could in fact get the output in analog form again. Now, the important thing is that you can implement something more complicated. For example, if you want to have an integrator, you instead of just multiplying it the error by a gain, you multiply it by a gain and also integrate it. In that case, you are effectively integrating E. So, E is equal to, let this is x, then this is dx by dt, and x is equal to integral of E dt. So, in fact, one of the ways of doing it is to in fact have a iterative recursive algorithm which calculates xk from xk plus 1. So, you in fact get each sample E, this is of course discrete time. Remember, computer does things in discrete time, k represents a sample of the discrete time. So, you, and if the time step between sample, the time difference between the sample is h, then you can integrate implement a approximate integrator by simply applying this algorithm. So, this is called an Euler algorithm, where you have emulated a continuous time integrator using a kind of a digital algorithm. Okay. So, the key steps of course are sampling at a high enough rate, so that you represent the signal appropriately. In fact, for example, in a voltage regulator for synchronous generator, you have got a 50 hertz waveform, you know. So, you actually, to represent a 50 hertz waveform, you need to sample it at least at 100 hertz, but you know, typically it is done at say about a kilohertz. Anything, if of course, one of the key points is that in case your signal contains harmonics or high frequency components, if you sample it, do not sample it at high enough frequency, you may in fact end up with wrong inferences in your digital system. In fact, for example, if this input here is supposed to be 50 hertz, but suppose it has got some spikes, and if you try to sample this and suppose you sample it at a low frequency, and you may actually get, for example, you sampled it at this point, then you sampled it at this point, and then you sampled it at some other point here, which is slightly, you know, these may not be occurring exactly at the peak. You may actually end up having a completely distorted picture of what is happening inside. So, if you sample it at low frequencies, this problem may arise. You may in fact think that this is a waveform which is of this nature, okay, which is not the case. The actual waveform is in fact a relatively low frequency, but it has got some spiky input. So, for example, if you happen to sample these, you may actually get a completely wrong inference. So, this is a manifestation of a phenomenon called aliasing, where if you do not sample at high enough frequency, you may have a problem. So, what we do usually is to knowing that if for example, I am going to sample at say 200 hertz, I make it a point to remove everything, all the frequency components which lie which are higher than 100 hertz. So, you actually remove first these spikes and then you sample. Okay. So, usually before sampling, if you have decided your sampling frequency is 100, say 200 samples per second, make it a point to filter out this waveform to remove any high frequency components. What high frequency components? Anything greater than 100 hertz, remove. If you do not do that, you may end up having wrong inferences when you sample. Okay. So, instead of thinking of this as a signal with a few occasional spikes, if you actually sample the spike, you may actually assume that your waveform itself looks like this, because you have only these values inside the digital system, and you may actually infer what the waveform is just based on this, and you may get in fact wrong inferences. So, this is a manifestation of aliasing. We have one simple question in your tutorial sheet which will try to bring out this aspect as well. In fact, for most regulators, although we do use lead functions, lag functions, the first order filter which we saw, also st upon 1 plus st if we want to remove some transient components, the steady state offsets, etc. These are all blocks which are control or are kind of transfer functions in the toolbox of a control system engineer, and he needs to use these appropriately so as to tailor make his dynamical response to what he wants. Now, typically if a control system engineer wants to achieve some kind of voltage regulation, he will use a proportional or proportional integral controllers. This may not be the only thing which may be existing in his control system, this may be a component. For example, what you are seeing in your screen here is a PI regulator. This may be in fact in cascade with some lead lag block, like how I had shown you here. This is what is known as a proportional controller. It gives an output proportional to this error. It's called a proportional controller in cascade with a lead block. Okay, lead or lag depends on whether T1 is greater than T2 or T2 is greater than T1. So, this is in fact, so the the system designer here in this case has chosen a proportional controller and a lead lag block. He could in fact use a PI controller, proportional integral controller, and a lead lag block, or just a P controller, or just a PI controller, or just an integral controller. It really depends on what kind of whether the control system he has in place satisfies some of the constraints which he has given. Now, typically the kind of constraints which control system designer will be faced with is one, you should be stable, the control system should be stable. That is the absolute primary kind of requirement which you can have. For example, if you have got a small child weighing a kilogram of rice, and if his brain is not trained to weigh the rice properly, you will find that he may just never settle down. The pans may sometimes be in one end, can be unbalanced on one side and then the other side and so on. So, you can actually have oscillations and instabilities. So, you will never reach an equilibrium. That is certainly not what a control system engineer wants. So, the first primary aim of a control system engineer is stability. The other aim is what is the kind of transient response he wants, how quick you want to settle down, what kind of inputs you would like to respond to, and what are the inputs you would not like to respond to. For example, you would like to make the controller responsive to a certain degree. For example, if you are driving a car, you would want of course any kind of the actuator and control system to respond in the order of say a second or so, but certainly not nanoseconds or femtoseconds. Okay. So, you need a control system to have a fast response, but you need not require that the control system should settle down in nanoseconds or microseconds. You require say a more realistic goal of a control system which has got response times which are of the order of seconds. So, every control system has its own characteristic. A power electronic system, of course, you would like it to settle down in a fraction of a cycle, or say about a cycle or two of the fundamental waveform, typically say 20 milliseconds or so. So, what kind of responses you want depends on the nature of the control system. So, that is one more aspect. So, one is stability, one is the quickness of response. The third thing is what kind of do you expect any steady state error. For example, uh, you would like that in this case, for example, you would want that the measured value or the terminal voltage of a generator should be equal to the set point of the which you give. If you can tolerate a little bit of error, you can use some other kind of control system. If you want absolutely zero steady state error, one of the ways of doing it is using an integral controller. Remember that an integral controller has a proportional part, a PI regulator, proportional integral controller has got a proportional part as well as an integral part. This is Kp and this is Ki. After this, by mistake it has been given as the same value. Actually, it can be different. The values could be different. These are the gains. Okay. Now, remember that these are all differential equations. Actually represent differential equations, and the overall plant is also a dynamical system. So, all these parameters in fact affect the response. For certain parameters you may even get instability. So, there is a element of design which goes into how you choose this Kp and Ki. In fact, this integrator here has got the steady state gain of infinity. If I put S is equal to 0, this gain becomes infinity. So, the steady state gain is infinity, the transient gain is 0. So, if I put S tending to infinity, which is in fact the transient gain, gives us the transient gain, the gain becomes 0. Okay. So, an integrator has got a transient gain of 0 and a steady state gain of infinity. So, when you say I have got a steady state gain of infinity, what it means is that the input has to be 0 in steady state, because if the input is not 0, the output will become infinity. Okay. So, in fact, in another way of putting it is that the integrator, if the system is stable, then you will find that the integrator has driven the input to it to 0. Okay. So, if you got a PI controller, remember that the error is always driven to 0 in the steady state. So, as long as you are stable, if you are not stable, of course, you will never reach the steady state, but if you are stable, then this is actually driven to 0. So, a PI controller is one of the controllers which drives the steady state error to 0. Okay. So, this is also used in many control systems. In fact, usually one of the practical considerations in a controller is what can you achieve using an actuator. So, although these gains are in our hands, this Kp and Ki, by mistake this is written as Ki, but is in fact Kp, these two gains are in fact could be distinct. This actually feeds the actuator, this is the controller. So, your brain and your actuator is your hand. So, your brain commands your hand. So, usually the command which your controller gives to the actuator is in fact should be compatible with the capabilities of the actuator. There is no point in actually having commands from your controller which are not at all compatible with the abilities of your actuator. For example, an excitation system can deliver say 200 volts to the field winding of a synchronous generator. In such a case, that is the maximum output you can get out of your converter for a given AC input. The converter is in fact the controllable part of an excitation system. It is fed from an AC source, and through the delay angle control we can obtain the control over the DC voltage of the converter. Now, if the AC voltage is fixed, there is a maximum limit to how much voltage you can get at the output of the AVR. And for example, if this output is 200 volts, that is the maximum possible output you can get out the converter, whatever you give your firing angle, the maximum value is say 200. There is no point in your controller, which is the automatic voltage regulator, commanding your converter to deliver 200 volts. It is not going to happen. So, typically there is your controller will have limits which prevent the output going beyond what the actuator can actually deliver. So, this is achieved using limiters. In fact, there are two kinds of limiters I show here. This is called a soft limiter. The soft limiter essentially just clips the output. So, even if this goes above the limits specified here, the output will remain within these limits. Okay. So, it will just clip the output, whereas this is another limiter which is called a hard limiter, in which case this the integration itself is stopped. Not only is the output limited, but the integration action also is stopped in case you exceed the limits. Now, both these limiters behave somewhat differently. For example, one of the examples which will be shown to you shortly here, you will see that you have got three integrators. This is in fact using the XCOS tool of Scilab. You can, it is a free software, so you can download it and you can see XCOS, and if you actually look at the, go to the internet, you can actually download it and you can find out, you can actually freely download it and do your simulations in this. In fact, these are three integrators. One integrator here is a plain integrator, it just integrates the output, there is no limit. The second is an integrator with what is known as a soft limiter. So, you have got a, the output is clipped to the limits shown here, and the third limiter here has got an internal limit which is in fact you know, it is a hard limiter. So, this hard limiter is in fact given here, it has got an upper limit of 0.5 and minus 0.5. Yeah. In this integrator there is no limit. Yeah, there is no limit here. In fact, the upper limits are placed so high, it is around 1000 and minus 1000, we will never reach those values. So, for all practical purposes in this simulation, this integrator is having no limits, but the output is clipped. So, the output is simply clipped. So, this between, so this is the same limit as we had specified for the integrator of the bottommost block here. The same limits, but this is a limit which is external, it is just a clipper, and this is in fact an integrator without limits again. Okay. We have specified the limits, but these are very high. So, for all practical purposes we will not reach those limits for the specific example which is given here. The input is a sinusoid. So, sinusoid with a magnitude of 1 and a frequency of 1 radian per second, phase is 0. So, actually start at t is equal to 0 also. So, this sine wave starts from t is equal to 0. If you integrate a sine wave which starts at 0, you will get the output as 1 minus cos omega t. Okay. So, you integrate sine wave sine omega t dt from 0 to t, you will get 1 minus cos omega t. So, that is what we expected the output of this. The simulation tool which is used, the simulation method which is used here is the one which is given in the library here. Can you just show the one method which is being used? Because we should show. So, this is using Rangekutta method. Of course, this is a plain integration, there is no this is not a closed loop control system, it is just a plain integration. So, this and the time step is in fact 1 millisecond. No, it is in fact okay. This time step is in fact specified outside. So, we will in fact, so we have a external wrapper program which actually calls this simulation, and this is also being, this will be of course uploaded as a part of the course material. So, you should be able to use this. So, if you actually use this system and do the simulation, you will find that the three outputs are in fact different. For example, you run this simulation and the output is given as shown here. The input is in fact the blue, in the blue, that is a sine wave starting from 0 and at t is equal to 0. You integrate this, you will get 1 minus cos t, which is in fact the waveform in pink here, and the output of the first integrator, that is using a soft limiter, is simply the black thing. So, you see that the if you look at this till 0.5, it follows this 1 minus cos omega t, but here it hits limit. So, it clips the output. You please pay attention to the black signal, and as soon as the output comes below 0.5, it lets it out again. Okay. So, as long as the output is between plus or minus 0.5, it allows it out. This is in fact a different, the red one is the output of the hard limiter. In fact, as soon as this hits the limit of 0.5, the output is in fact limited, but also the integration is stopped. So, this is an important thing, the integration is stopped. Because the integration is stopped, it remains, the integrator remains at this value, and as soon as there is a chance to come out of it, when is the chance to come out of it? When this input to the integrator starts becoming negative, immediately the limiter comes out of its limit. The important point is that whereas with the soft limiter the integration has not stopped, in fact the integration is going on, but is let out only when the limits come within the band which is specified, the output comes within the band which is specified, plus 0.5 and minus 0.5. Whereas here the integration is completely stopped till this becomes negative, because once this becomes negative there is a chance for the integrator to come out of its limit. So, it comes out of its limit and its behavior in fact is quite different. Okay. One of the interesting points here is that here the integrator is able to come out of its limit faster, because it is not gone on integrating, it does not go on integrating despite hitting the limit. So, actually a hard limiter makes a lot of sense in case you have got an integrator. Otherwise, what will happen is that even though no action is being taken because the output is being clipped, the integration is continuing. If you allow the integration to continue, it takes a much longer time to come out of the limits again. Okay. So, a plain soft limiter or clipper will take a long time to respond and come out of its limit, whereas at the first available opportunity the integrator will come, the hard limiter comes out of its limit because it has stopped integrating at this point. Okay. So, this is a subtle difference between the two limiters. You can look at this program which will be uploaded as a part of a material and try to understand what it does. Yeah. Now, another kind of control system which we have is in fact what is known as a governor. Remember that just like an excitation system, the plant or the actuator for changing the mechanical power is in fact the, in case of steam turbine, the boiler and the turbine are the two things which actually control the output of the turbine, the power output of the turbine. In case of a hydro plant, you can actually change the gate position, and the hydro turbine is in fact converting that to converts that mechanical energy into into driving the generator. So, the hydro turbine in fact can be controlled by what is known as the gate position, whereas a steam turbine can be controlled by changing the control valves which or the inlet to the turbines, okay, steam inlet to the turbines. Of course, in a steam turbine you will note that as you open the valves, more steam flow is there, and because there is more steam flow, the mechanical power in fact increases. Of course, if you keep the valves open, the steam flow will increase, but eventually the pressure will start falling, and in order to keep the pressure intact, you will have to have the boiler generate more steam. So, of course, the point really is that if you demand more power, you need to actually burn more coal. So, that is the basic point, which of course makes a lot of sense and it is intuitively comforting. In a hydro turbine, you have to let in more water, and the gate position in fact opening, you increase the water inlet to the turbine, increase the amount of water flow in the turbine, and you will find that the power increases. So, the main thing is of course that the turbine is the thing which actually controls the output power, the turbine along with the boiler in a steam generating plant, and in case of hydro turbine, the reservoir and the the gate of the turbine, hydro turbine actually control the amount of power. Now, the gate position itself or the steam valve position itself has to be changed, and that requires some amount of power, and that is usually so you have got some servo control system which actually tries to change the gate position. So, you require a little bit of mechanical power, rather a bit of force to actually change gate position. So, that is also there is a motor which does that, and what you the control system of that is of course can be actually implemented digitally. Nowadays, many of the control systems are in fact implemented digitally, where the speed is measured and a control system like a speed governor in fact can closed loop control system in fact controls the valve position or the gate position. In fact, the speed you can also can also change the load reference manually. You can change the amount of the gate opening manually by, if you for example want to ramp up the power, you can do that also. But the governing system is in fact a speed regulating mechanism. Okay. So, you can change the, just like how you change the field voltage of a generator to keep the terminal voltage constant. Similarly, you can change the mechanical power output of a turbine so as to keep the speed constant or near constant. Okay. It need not be exactly constant. Now, a single synchronous machine connected to a synchronous machine connected to a load, you would need to control the speed. The reason is simply that if you load the machine, you need to as you load the machine electrically, you will find that the electrical torques which actually tend to decelerate the machine, and unless you increase the mechanical power to the turbine, you will not be able to maintain the speed. So, you actually have to measure the speed in some way, compare it with a set point and adjust the mechanical power, so that the speed does not decline to an unacceptable value. So, for example, if you have got an isolated generator connected to a load, for example, if there is a generator, isolated generator connected to all the electrical systems in this classroom, you will find that as I switch on one light, you will of course have to increase the prime mover input. If you are using a diesel generator, you will have to actually burn more diesel, so that you get more torque, so as to cater to this load. Now, so this kind of system is called a speed governing system, and this is a control system which has to be there if you have got a generator connected to a load. Okay. Later on we shall see that in a large grid, not all generators may have governors, a few of many of them may have, but if you have got a single generator then connected to a load, you have to have a speed generator. That particular generator has to have a speed governor, otherwise it will be difficult to cater to varying loads. Okay. Otherwise, moment you connect a load, the speed will reduce, and if the speed reduce, the frequency of output will increase, will change. Okay. So, this is one of the problems which or if for the opposite also can happen, if a sudden load throw, the speed will go on increasing, and to avoid that you need to have some kind of control mechanism. So, the idea is the same as in an excitation system. You have got a closed loop excitation system, a closed loop speed governing system. Remember that the turbine itself is not what do you call if you for example change the valve position, even changing a valve position requires a bit of dynamics of the servo mechanism which actually changes the valve position. The turbine itself, the output does not immediately change. In fact, there is a kind, for example, if the gate position is changed, this is a kind of a per unit diagram. If there is a per unit, for example, a certain, this is a kind of normalized block diagram of a turbine for small changes in the gate position. If you change the the valve position, if you change the valve position in a steam turbine, you will find that the output PM changes after some time, and in fact, the behavior is determined by this transfer function representation. This is of course a kind of a representation for small disturbances. The typical time constants associated with it are on the larger side. You will find that because of this reheat component, the time constants can sometimes be quite large, the overall time constants. Okay. So, this is the control system, this is the model of the turbine, okay, small for small changes especially. So, this is the model of the turbine. In addition, of course, this is not the control system, the turbine is in fact the control system actually changes the valve position. Okay. For a hydro turbine, a very simplistic model is a simplistic model for again for small changes is a simple transfer function of this kind. If you change the gate position, is all normalized of course, that is 1 per unit gate position gives you 1 per unit mechanical power. The steady state gain of this is, as you shall see, is by putting S is equal to 0, you will find that the output is equal to. So, the steady state gain is in fact 1. Okay. So, if you want to get 1 per unit here, you have to have a normalized gate position of 1. Okay. So, this is kind of a normalized position. Now, one of the interesting things about this model is that it is what is known as a non-minimum phase transfer function, or it has got a 0 on the right hand side of the complex plane. So, the 0 is S is equal to 1 upon T W, and although this does not mean that this is a stable transfer function, but in fact, 0 is on the right hand side, and it has got a peculiar characteristic, that is, if I give a step change to the input of this. Of course, remember that in these kinds of systems one cannot give step changes. This is T W by 2 and this is T W S T W. And if I try to increase it, let us for the sake of argument say it is a step change, increase here. An interesting thing is that the steady state gain is 1, this is by plugging in S is equal to 0, but the transient gain which is obtained by plugging in S is equal to infinity is in fact 2, minus 2. So, if I give a step change in input here, the output is in fact like this, it goes down and then goes up. So, actually if I open the valve, initially the power in fact reduces, but later on in steady state of course it goes to the position or the power level which we want. Now, this is called a non-minimum phase kind of transfer function. The initial movement in fact is because it has got a 0 on the right hand side of the complex plane, S is equal to 1 upon T W is on the right hand side of the plane. Of course, this is a stable system because the pole is of course on the left hand side of the complex plane. So, it is not an unstable response, but you see that it goes to minus 2 in case I give an input of 1. Now, of course, remember there are limits to this model itself. This model which we have got of hydro turbine is highly simplified. Okay. The model of the behavior of the power as you open the gate is highly simplified in this transfer function, but even with this, for argument's sake, if we take the simplified transfer function, it has got quite a peculiar behavior. It the power in fact may drop. Electrical analogy is like this. Suppose you have got an inductor connected to a resistor like this. The power output of this resistor is in fact given by V square by R in steady state. Okay. But suppose I have got and I connect another resistance here. So, R and R. If I connect this resistance, then in steady state the power is V square by R by 2, that is 2 V square by R. Okay. But the instant I connect this, in fact, as soon as I connect it, the current here does not change because we have got an inductor here. Okay. Because there is an inductor, current remains the same. What is the current? The pre-disturbance current V by R. Okay. So, this current is flowing into a resistance of, so I square R comes out to be R by 2. So, what happens is that the instant where you switch this on, the power dissipation in this bank of resistors in fact reduces and reduces from its earlier value, that is V square by R, and after some time it becomes twice the value initial what this value is. So, this is an example of a system which behaves something like this. So, initially the power reduces and thereafter it increases. Okay. So, this is a unusual kind of transfer function, and if you are actually if you are a controller, suppose you are a human controller, you should be a bit careful when you are designing a control system for this, because the moment you do something, initially it goes in the opposite direction, which may transiently confuse you, and if you react to that going in the opposite direction by unnecessarily overreact to it, so to speak. You may go on worsening the situation. Okay. So, you may actually say, oh, it is going the opposite direction, let me put more gain or let me increase my control action, and that would be unnecessary. In fact, if you are faced with this kind of control system, a good idea would be just to wait for some time for the control system to respond. So, in fact, these kind of the control system designed for speed governing in a hydro turbine model, in fact, has initially gives a low gain. In fact, it tries to not overreact to what is happening and then increases the gain. So, you have got what is known as a transient droop in a hydro generator. This is something you can try to read up in a book which discusses this. Yeah. In fact, this transient droop compensation in a hydro turbine is discussed in books on power systems. I can refer you to the book by Kundur on power system stability. The turbine and governor can then be modeled. So, the control system is in fact this. This slip is nothing but the speed error, and this is given to a gain, and it may have in fact lead or lag circuit. Depending on the value of T1 and T2, you can adjust the response, and this is in fact the servo mechanism also can be modeled. There may be actually limits to how fast you can obtain change the valve position. So, this is in fact just a model, okay, of the governor plus the servo mechanism which actually changes the valve position. Okay. Remember, the valve position movement also cannot be done just in an electronic signal, it requires another actuator to actually change the valve position. And for a hydraulic turbine, it may be slightly more complicated. As I mentioned here, you may actually have a gain which is somewhat low. In fact, this is you may actually end up having a kind of a control system which kind of has a behavior which is different for fast changes and for slow changes. Okay. So, this is something which I will not discuss here. You can try to model this control system on XCOS, which is showed here, and see what behavior, how the behavior is when you have different beta and gamma. Okay. So, of course, this is a kind of ends a rather brief discussion of the governor. Governor is something which changes the valve position or the gate position in a turbine so as to regulate the speed. Remember that the error in the signal is passed through a controller. Here I have shown a proportional controller. You can also have a proportional integral controller. In case you use a proportional integral controller, it will drive the slip to 0. So, this kind of controller is called a isochronous governor, in which a generator is strictly regulated to the reference speed. In other words, it drives the steady state error to 0. Okay. So, this is something we discussed some time back. A PI controller, if you use, this slip will be driven to 0. Here of course, I have shown a proportional controller. Okay. So, in fact, if you use a proportional controller, to get any output, you need to have an input. So, let us just get back to what we discussed some time back. If you use if you do not use this integral controller, you have got what is known as a proportional control. Let us say this is Kp, not Ki here. So, if I disable this, the controller is simply a proportional controller, and interesting point about proportional controller is that if you want to get an output, you should have an error. So, a proportional controller, to get an output which is non-zero, it has to have a small error. Well, small or big depends on this gain. So, for example, in an excitation system, if you want to get say 2 per unit or a certain value of excitation voltage to achieve a certain UREF, you will have a small error. Okay. So, U measured will never be exactly equal to UREF if you have got a proportional controller. If UREF says 1 per unit, you will find your measured value may be slightly lower than 1 per unit in case you use a proportional controller. So, this kind of controller is said to have a slight droop. It is not regulating U measured to UREF exactly. Okay. So, a proportional controller always has some steady state error, and this error is often characterized by what is known as a droop. That is, if you want to more output y, you will have to live with more error here. Okay. On the other hand, an integral control, if you got a controller which has got an integral controller, it drives this to 0, provided of course your system is stable, and in that case the error here becomes 0, and if the error here is 0, despite that you could have an output, because the integrator is something which retains, because it is an integrator, it retains what it has done. So, you can have an output despite having this equal to 0. So, a isochronous governor would use an integral law. Here I have shown a proportional law. So, proportional law is also called a droop controller. That is the especially if the proportional controller has got small gain, then to get a certain output you need a larger error. Okay. So, you will never be able to achieve a 0 error, that is you will never able to achieve perfect regulation, and that is called droop regulation. Now, in case you have got an isochronous governor, you will have an integral controller, and this can be made to go to 0. Okay. Now, you may ask a question that why talk in terms of proportional controllers when you can have an integral controller? Well, if you have got a single generator connected to a load, you will find that in fact, you can use isochronous governor which represents, which in fact regulates the frequency quite well. In fact, it drives the steady state error to 0. But in case you have got many synchronous machines connected to each other, we shall see that a droop control strategy using proportional control is in fact more sensible, because without communicating with each other, the governors, the generators can in fact share the responsibility of regulating the common frequency. Now, one of the things we will learn later, that when you connect synchronous machines together, they get synchronized, the frequencies eventually in steady state become equal, okay, if the system is stable. And in such a situation, if you have got all generators having or many generators having a governing system, then the question arises, how do they share the responsibility of maintaining frequency, how much should each generator increase its, or how much should each turbine in fact increase its generation. And in fact, then it becomes more sensible to use a droop kind of strategy rather than integral or isochronous strategy in a speed governor. This is something we will discuss later on when we talk of interconnected grids. However, if you have got a plain synchronous generator, you can actually regulate the speed exactly, just a single synchronous generator connected to a passive load, like for example, in this classroom if you have got a diesel generator supplying this load, you can very well use a proportional integral type controller or an integral type controller, provided it is stable, and regulate the frequency exactly, that is drive the per unit slip. Slip is of course difference frequency, you can drive this to 0. Okay. So, these are some of the concepts which are important. You can have hydraulic or steam governors, and of course, since the plant model is slightly different for a steam or a hydro turbine, the governors also are different. As I mentioned, the response of a hydro governor to a change in gate position is quite different from the behavior of a steam turbine to a change in the valve position. So, in the next class we shall do two things. One, we shall learn about load characteristics, and also look at another method of generating power, that is wind energy. Thereafter, we shall consider the behavior of grids, but before that we will have a lecture on transmission lines, then we will see interconnected grids, and then thereafter we shall bring a course to an end. So, that is all for today's lecture.